Hello everyone, and welcome back to the AI Research Roundup. I'm your host, Alex. It's May 3rd, 2025, and today we're looking at an interesting ICLR conference paper titled Data Shapley in One Training Run, published back on January 22nd, so just over 3 months ago. This paper introduces a really neat idea called In-Run Data Shapley. It's basically a way to figure out how much each piece of training data contributes to one specific training run, especially for large models. Okay, so how efficient is this In-Run Data Shapley method? Well, this table compares different implementations using throughput. Basically, how many data points get processed per second during training. You can see regular training is around 76. The first-order ghost method is remarkably close at 70.5, which is fantastic. The second-order ghost is slower at 34.4, but still much faster than the direct methods. This really highlights how the ghost techniques make this approach computationally practical. Alright, so we saw how efficient these methods are, but how accurate are they? Well, this figure directly compares the first-order and second-order approximations to Monte Carlo estimations of the In-Run Shapley value. Look how closely the points hug that diagonal line, especially for the first-order method. The very low RMSE values confirm this. It shows these efficient approximations are indeed capturing the data contributions with high fidelity, which is great news for their practical use. Building on that accuracy, this next figure shows a really practical application, so plots test loss over training iterations. This solid blue line represents the original training run. Then, the dashed and dotted lines show what happens when you remove data identified as low value, using In-Run Shapley or influence functions. Look how the cleaned runs converge faster, reaching the target loss about 25% quicker. This really highlights the practical payoff for data curation. Okay, so beyond just speeding things up, In-Run Shapley also reveals how data contribution changes over time. This figure shows the contribution percentage from different domains, like PyleCC, Ruoxi, PubMed, across training steps, specifically when validating on math text. You can see general corpora contribute more early on, but then domain-specific sources like argciv become dominant later. This really shows that data value is dynamic. It depends on the training stage. Okay, so this figure visually contrasts the old way with the new in-run method. Traditional Shapley, on the left, is computationally brutal, requiring countless full retrainings on data subsets. In contrast, the in-run approach on the right works within a single training run. It calculates the contribution for each mini-batch as the training progresses, acting like a contribution accountant, making it far more efficient for large models as we saw earlier. So, this figure really breaks down how that efficient in-run method works, building on the contrast we just saw. Rather than evaluating the entire training process, it decomposes it into individual gradient updates. For each step, it calculates a local Shapley value based on that batch's contribution to reducing validation loss, then sums these up over time. This iterative decomposition is the core idea making the computation tractable for large models. So, wrapping up on this work, we've seen how In-Run Data Shapley cleverly breaks down the contribution calculation into manageable steps within a single training run. It's remarkably efficient, highly accurate, and offers practical benefits like faster convergence through data curation. It really provides a feasible, principled way to understand data value for large models, even revealing how contributions change over time. That's all for this segment. Thanks for tuning in.